I have discussed elsewhere how to reduce emissions from the cement industry. We all know that cement, steel, aluminum are some of the highest emitting industries, and they are growing in demand because developing countries like India and China will keep doing infrastructure, housing, commercial buildings, and so on. And even the US, whose infrastructure has become old, is actually doing climate action through updating the infrastructure. There is a retrofitting aspect which is supposed to make it more resilient, not necessarily always focused on reducing emissions, but nonetheless, this gives us a good topic to talk about. How to recycle cement and steel. So here it is a nice article. I'm not an expert on this, but my goal is always to bring important topics at some introductory level to you so that you are also aware of the issues and the potential solutions that are being looked at, without having to be a technical expert, but technical experts can go and follow up on the details if they want, right? So this is joint recycling of steel and cement that cuts CO2 emissions. So the real paper is here, and its news and views article is here, which is how science and nature tend to do it. So joint recycling of steel and cement cuts CO2 emissions. Cement can be reused by including it as a component of steel recycling. This opens the way to an industrial partnership that improves the use of materials and lowers carbon emissions, but only if waste resources are well managed. Right now, buildings are brought down either for redeveloping them into bigger buildings or because they are too old and have to be rebuilt. But what happens to that material that's collected from the demolition, let's say, of the buildings? It's hauled away and you don't know what happens to it. Often it's created to recover land at coasts and expand or have living spaces in terms of usable land and so on. So this article provides a nice summary figure. It's the news and views, which is what they tend to do. So recycling of cement in partnership with steel manufacturing. A is in conventional cement manufacture, limestone is heated, calcined. So calcium carbonate is split into basically calcium oxide, which is what is needed for the clinker and the cement process, and then it's mixed with silica-rich clay in a kiln. In conventional production of new steel, iron oxide is chemically reduced by carbon monoxide in a blast furnace, and lime made from limestone in a kiln reacts with the components in the ore that would otherwise lower the quality of the steel. The manufacture of cement, lime, and steel directly produce carbon dioxide in addition to the CO2 emitted if fossil fuels are burned to heat the kilns and furnaces. So you can reduce energy consumption or use renewable energies, but then the process itself is CO2 heavy. Scrap steel can be recycled in electric arc furnaces, which heat materials electrically, but methods of recycling cement have been lacking. In B, we are looking at Durant et al.'s report, which we'll read next. So Durant et al. Report that used cement can partly substitute for lime when steel is recycled in an electric arc furnace. The lime and used cement is converted into a slag material that can be used as a recycled cement. The process avoids many of the CO2 direct emissions shown here. Right? So if you have renewable energy to do all this, and life cycle analysis shows that this is still comes out as lowering total emissions, then of course it's useful, and that it has to be scaled up, of course. So this news and views article, they always end up with a nice caveat at the end to say whether the work is all positives or if it has some missing points. So here, establishing a pathway to cement recycling has not been easy in the past. The author's findings not only suggest a way forward, but also raise the prospect of forging a means for co-production between two of the industries that generate the highest global CO2 emissions, cement and steel. Efforts such as these to extract the most value from resources scaled up for mass production and tailored to local needs combined with strategies for reducing associated environmental impacts, will be key to decarbonizing society. So they give it a positive overall impression. So the article itself looks at electric recycling of Portland cement at scale, which means you have to do it at large enough scale to have an impact on the overall reduction in CO2. Cement production causes 7.5% of the global anthropogenic CO2 emissions arising from limestone decarbonation and fossil fuel consumption. Current decarbonation strategies include substituting Portland clinker with the supplementary materials, but these mainly arise in emitting processes, developing alternative binders, but none yet promises scale or adopting carbon capture and storage that still releases some emissions. So people are obviously addressing the cement issue. There are green cement ideas from Sweden and so on, and there are of course green steel ideas using hydrogen, renewables, etc., etc. However, used cement is however, my pronunciation tends to be garbled because I'm not a native speaker. However, used cement is potentially an abundant decarbonated feedstock. Here we show that the recovered cement paste can be reclinkered if used as a partial substitute for the lime dolomite flux used in steel recycling nowadays. The resulting slag can meet existing specifications for Portland clinker and can be blended effectively with the calcined clay and limestone, which is not recycled, direct new production. The process is sensitive to the silica content of the recovered cement paste and silica and alumina that may come from the scrap, but this can be adjusted easily. We show that the proposed process may be economically competitive, and if powered by emissions-free electricity, can lead to zero emissions cement while also reducing the emissions of steel recycling by reducing lime flux requirements. Jumping to zero carbon cement is a bit ahead, but obviously there is a pathway. The global supply of scrap steel for recycling may treble by 2050, and it's likely that more slag can be made per unit of steel recycled. With material efficiency in construction, future global cement requirements could be met by this route. So you need to worry about building material, building efficiencies, maybe wood for building, etc., which I've discussed elsewhere in the drawdown course, but here we are only focusing on recycling Portland, but as a combined steel and cement recycling process. So many technical details are there that I won't go into. I'll just jump ahead to discussion. As I said, this is an introduction to a very important topic, so you can follow up if you are interested in this. What is the discussion? All processes, norms, practices, and habits in the construction industry are centered around Portland cement, the most dominant process. Therefore, it would be difficult for any new material to replace it unless it had considerable advantages. As Portland cement is made from the most abundant elements in the crust of the earth, it's unlikely that any potential substitute could be cheaper or available in equivalent volume. Despite its requirement for high temperatures, the present production of Portland cement is already energy efficient, so you cannot reduce energy emissions, exploiting molten iron and aluminum oxide phases to transport ions. So Portland cement is already energy efficient, exploiting molten iron and aluminum oxide phases to transport ions. Therefore, the only practical avenues for decarbonizing cement production depend on altering the range of allowable compositions using new SCMs or charging process by which cement is produced. Recycling Portland cement as proposed here saves the process emissions and the bulk of the energy required for production. The proposed industrial symbiosis needs careful development, but both steel making and clinkering processes require careful chemical tuning, but as steel is more expensive, its requirements would dominate decision making. Substituting RCP for lime flux, which is another approach, should make no marked change to the steel quality or the air pollution created during the EAF electric arc furnace process. So the existing regimes of exhaust scrubbing should remain appropriate. In co-production with steel, cement would have a higher iron content because of rheological requirements for slags, how smoothly it flows, however, viscosity. However, our requirements show that the cement composition can be tuned with additions of lime to target optimized blends. The cement produced using this new process can have a higher alite fraction than previously published results or commercial clinker. So each one of this is shown in the I have a knock on the door, so let me stop for a second and conclude in a minute. Sorry about that. These things happen when you work from home. So we were discussing these ideas, and the discussion talked about how things are already going on in terms of using new SCMs, which are supplementary cementitious materials that basically try to reduce the use of the clinker, and of course RCPs are recycled cement paste, which also substituting it for lime flux should make no remark. So basically we're thinking about not new clinker but recycled cement paste, which is what the topic is all about. So here we are going to conclude with this. This study demonstrates that, my computer is dying, so it doesn't do properly the click on the mouse. Anyway, this study demonstrates that using existing industrial scale equipment, it is possible to recycle Portland cement into Portland cement in an all-electric process. The process can be operated as co-production with steel recycling or for the exclusive production of cement itself using an electric arc furnace with a small untapped pool of molten steel. The process is fundamentally a material substitution within existing processes, equipment and standards, and so it could scale up rapidly since no new technology is needed. Of course, you have to collect the concrete that has been produced from demolishing buildings or whatever, and transport it to these places where you can do the recycling. It creates the first zero emission alternative to existing cement production, to our knowledge, which accounts for 7.5% of the present anthropogenic emissions. So these kind of theoretical suggestions obviously need practical life cycle analysis kind of things, but let's say you have to transport a lot of used concrete to these recycling or new cement production plants, and how co-located the steel has to be or how steel has to be transported to do the joint recycling and so on depends on maybe electrifying the transportation process itself and so on. So we have to keep on closing the loops in the circular economy or the life cycle analysis so that we actually can decarbonize cement and steel, because they are continuing to grow and they will continue to be in demand for a long time. Okay, so I'll leave this here. Again, just remember, I'm just trying to give you a brief introduction to the nice, interesting topic here, that latest finding in this direction. Okay, see you in the next topic, which is also very interesting, which also is not something I'm an expert in. It's called "What Will the Future Refineries Look Like?" Right? So come back and meet me there.